Welcome to Precalculus, video lecture number 16 on the graph of a rational function. So we're going to be putting together all of the ideas covered in previous lessons concerning rational functions so that we can make very detailed and lovely graphs. So here's the steps for sketching the graph of a rational function. Assume your function f of x has the form g of x divided by h of x, where both g and h are polynomials that have no common factor. And we discussed in the previous lesson how important it was to make sure that your rational function is completely simplified. Otherwise, you might think that some points are vertical asymptotes when they really aren't. Okay. Now, factor the numerator and denominator and find the domain of f of x. You want to do that before you've canceled out any common factors. So make sure you find the domain before canceling. Then you're going to find the x-intercepts and plot them, find the y-intercepts and plot them. Then you find any vertical asymptotes. Sometimes you might have more than one. Remember, we find those where the denominator h of x is equal to 0 after your rational function has been completely simplified. And when you sketch that asymptote x equals a, use dashed lines. And then again, you're going to find the horizontal asymptote, which we went over previously, and find the equation of it. Make sure you write y equals c, or whatever the constant is, sketch it with dashes. If there's no horizontal asymptote, then sometimes there's an oblique asymptote. To do this, you're going to use long division. And then if there is a horizontal asymptote or oblique asymptote, you need to determine whether or not it intersects the graph. Now, this might seem strange to you, but I did mention before, this is possible on occasion. Now, a graph will never cross its vertical asymptote because vertical asymptotes come from x values that are not in the domain of the function. But since horizontal and oblique asymptotes describe the end behavior of a graph, what it does in the long term, it might, in the short term, cross it. Yes, rebellious little graphs do that. So I'll show you how to find whether or not that happens, and then you would plot it, and then sketch the graph of f. Now, it's up to you how much more, plotting you want to do, and I'll show you my reasoning process. I like to plot the minimal number of points possible to make a graph, and most of the time, with the intercepts and everything, it's enough. Every now and then you have to do a little bit more work. So I'll talk you guys through it, don't worry. And if you're one of my students, I'll give you all of the steps when you need to do a problem like this on an exam or something. Okay, so here we go. Let's dive right in. Sketch the graph of the following functions. First one is f of x equals x plus 4 divided by x squared minus 4. How lovely. Okay, so let's fully factor first. So step 1, I'm going to write f of x as x plus 4 divided by, the denominator is going to factor into x plus 2 times x minus 2. So let's list the domain right now. The domain is going to be all x's such that, notice, the denominator would be 0 at 2 or negative 2. So those are our restrictions. X cannot equal plus or minus 2. Good. Now let's move on. Let's find the x-intercepts. So x-intercepts come from setting f of x equal to 0. So 0 equals x plus 4 over x squared minus 4. And to solve this equation, the next step would be to clear out the denominator, right? So I'd multiply both sides by x squared minus 4. And I want you to notice something that happens in the next step. I have 0 on the left-hand side because 0 times x squared minus 4 is just going to be 0. And then I have x plus 4 on the right-hand side. And here's what I want you to notice. That's the numerator. And that's going to happen every single time. When you're finding the x-intercepts or the zeros of a rational function, all you're finding is where the numerator equals 0. Because where the denominator equals 0, those points are not in the domain, and you end up clearing it out anyways every single time, just like we did here. Okay, so if you want to save yourself seconds of your life that you'll never get back, just go straight to setting the numerator equal to 0. Okay, very cool. Now I get x is negative 4, But remember, that's an intercept, so write it as an ordered pair, -4, 0. Nice. Next, we need Y-intercept, if there are any. Let me underline this. Okay, so step 3, Y-intercept. Remember, we get the Y-intercept by plugging in or substituting 0 for x, opposite variable. So f of 0 is equal to 0 plus 4 over 0 squared minus 4. So that's 4 divided by -4, which is -1. So my Y-intercept is at 0, -1. Always write those as ordered pairs. Lovely. Let's see now. Step 4 was to find any vertical asymptotes. Okay, well, this is in reduced terms, right? Nothing's going to cancel, so I'm just going to list the zeros as equations. Those are my vertical asymptotes. So they are at x equals 2 and x equals -2. Good. Step 5, horizontal asymptote. Okay, remember the rule. You look at the rational function and you identify the degree of the numerator and the degree of the denominator. So degree of the numerator is 1. Degree of the denominator, since we have x squared, is 2. Anytime your rational function is bottom heavy, meaning the degree of the denominator is larger than the degree of the numerator, your horizontal asymptote is at y equals 0. Game over. Don't do anything else. It is what it is. Okay. Did we do everything that they wanted from us? Let's see. We didn't check if it crosses the horizontal asymptote. My goodness, that could be life-changing. So here we go. You say to yourself, all right, does this graph cross the horizontal asymptote? So we're checking if it crosses the horizontal asymptote. I don't know. If it does, that would mean that at some point, my function would need to equal 0, right? Since the horizontal asymptote, the equation is y equals 0. If my graph were to cross it, then I'm really asking myself, does f of x ever equal 0? Well, yes, we found the x-intercepts at -4, 0. So it does cross. Oh, wow. That won't always work out that way, so don't worry. I'll show you more examples. And now let's put everything together. Okay, so put the asymptotes in, put the intercepts in, and then from there we'll decide if we need to plot more points. I'll show you how. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. That should be good. 1, 2, 3, 4. Okay, vertical asymptotes are at 2 and -2. Beautiful. And then we have horizontal asymptote at y equals 0. So I'm just going to draw a little extra on the x-axis so I remember. And then intercepts, we have -4, 0 and 0, -1. Okay, looks good. Now here we have to get one thing straight. There's 3 pieces to the graph. What do I mean by that? I mean this is piece 1, this is piece 2, and this is the third piece. Okay? Now in the first piece, your graph only has 2 options. It's going to cross the x-axis right there. It's either going to do it this way and then approach the horizontal asymptote, or it's going to do it this way. How do I know that's true? Well, think about what else could happen. Okay, well, it's got this vertical asymptote, so it has to approach it. I know it's going to cross here. It can't come back and cross again because we found the one and only x-intercept. The one and only x-intercept is right here. So I know it's not crossing anywhere else. Plus, eventually it has to approach the horizontal asymptote. It can't just keep going down forever. That makes no sense. Remember, the horizontal asymptote tells you the end behavior. So in the long run, the graph does have to approach it. All right, so for our 2 options, I basically don't know if it's coming from above or if it's coming from below. What can I do? Well, I can test a point in the function. Maybe something right here at -3. I could test and see, is f of x above or below the x-axis? So So let's see here. I'm going to get rid of that. Let's test with x equals -3. Okay, so f of -3, that's going to be, excuse me, -3 plus 4 divided by -3 squared, so that's going to be 9 minus 4. So this is positive 1/5. I don't really care what number it is. All I care is that it's positive. So at -3, it's positive, which means, I know what's going on. The graph is coming down from above the x-axis here, and then it hits through -4, and somewhere it's going to keep going down, and then it has a change of heart, and it goes, oh wait, I have to go back to the horizontal asymptote. Here I go. Now, where exactly it turns around, don't stress. When you're in calculus, you're going to find exactly where that local minimum is. But for our purposes right now, as long as you get that end behavior right and the overall shape, then you're good. Okay, I just want to make that look more curved. I'm not thrilled. Okay. Okay, good. Nice. Arrows on both ends. Okay, segment number 2. I actually don't need to plug anything in. Let me explain to you why. Look at this. Okay, so for the middle portion, you have a few options. Let's think about it. I'll give you samples. You tell me what's wrong with each of them. This is an option. We could have something looking like -x cubed smashed in there. What's wrong with it? Well, look, I just crossed the x-axis. That's not allowed. I have the one and only x-intercept. Do you remember where the only x-intercept is? It's right here at -40. So we're not allowed to cross the x-axis anywhere else. Okay, let me give you another option. Tell me what's wrong with it. Why isn't that possible? Again, I can't cross the x-axis anywhere else. We only have that one x-intercept. Okay, so it's not looking like x cubed. What if it looks like a parabola, smashed parabola between those two asymptotes? Nope, again, we got a problem. Look at us crossing the x-axis. Not allowed, breaking the rules. The only other option that works is you have something that looks like a downward opening parabola, okay? Is it exactly symmetric or not? You don't need to worry. You're just in pre-calc. When you get to calculus, you're going to figure out, because there's some options. This might, have a max a little bit later on and do something like this, but still have a general shape where it's opening downwards. You don't have to have such worries in your life, so enjoy this carefree moment in pre-calculus. And we're just going to graph it opening downwards somehow, okay? So I'll make it a little asymmetrical just so you don't assume necessarily. But it might look like a parabola as far as we know. Okay, so see, I didn't have to plug in any points there. If you want, you can, but you don't need to. Lovely. Okay, last portion. Portion 3. So here's our options. You tell me what makes sense, what doesn't make sense. Well, I could either have one like this. That's certainly plausible, right? I didn't cross the x-axis. It's not going to go like this. We have to approach the horizontal asymptote, and we can't cross the x-axis. Or it could look like this. We don't know. So how do we figure out? We're going to test a point again. Yes, we are. So let's test this time with +3. Okay, so we'll test with x equals +3. And I'll plug that into the original function. So f of 3 is 3 plus 4 over 9 minus 4. I don't care what number it is. Remember, I just want to know if it's positive or negative. So since it's positive, that means it's above the x-axis. So this piece of the graph is going to come down and then just approach the horizontal asymptote, y equals 0, like that. So when your graph has 3 pieces, remember, the outer portions semi-resemble 1 over x. Do you guys remember what 1 over x looks like? So 1 over x, burn this in your brain. 1 over x is like this, right? And then the middle portion, your options are something like this, something like this, something like x cubed, or negative x cubed. And you got to figure out what it is. All right, looks good. Let's clean up this mess here. And that's your final answer. Okay. Let's look at some more examples. These can be tricky. F of x equals 2x squared plus 4x minus 48 divided by x squared plus 3x minus 10. Okay, let's rewrite this function completely factored. So f of x equals, notice I can take a 2 out of the numerator, so let's do it. X squared plus 2x minus 24 over x squared plus 3x minus 10. And then that actually factors, right? Everything factors. How fun. We have 2 times x plus 6 times x minus 4 over x plus 5 times x minus 2. Nice. Okay, so let's go ahead, list the domain. So the domain, we're going to have 2 restrictions, right? Can you see the denominator is going to be 0 if x is negative 5 or 2. So my domain is going to be all x's such that x does not equal negative 5 or positive 2. Good. What about x-intercepts? Remember, you can just go straight to looking at where the numerator is 0. So if I want to find the zeros of the numerator, ooh, it's already factored for me, easy breezy. That constant of 2, that does nothing. So the x-intercepts are going to be at negative 6, 0 and positive 4, 0. Nice. What about the y-intercept? For the y-intercept, it's actually easier if you go back to the original version of f of x before you factored. If you want to plug in 0. So f of 0, can you see? You're just going to have negative 48 over negative 10. So that's 4.8. So your y-intercept is at 0, 4.8. Let's box all of this good stuff because we're going to have to plot the intercepts. So let's make sure they stand out. Okay, now let's list our asymptotes. So vertical asymptote, do we have any? We sure do. We've got 2 of them at x equals negative 5 and x equals 2. And then what about our horizontal asymptote? Do we have one? Well, look back. You can look at the original or the factored one. I think the original is easier. So degree of the numerator is 2. It's degree 2. Degree of the denominator, also degree 2. Do you remember what the rule is? When the degree of the numerator is equal to the degree of the denominator, you take the ratio of the leading coefficient. So you're going to take 2 divided by 1, and that gives you the equation for your horizontal asymptote. So it's at y equals 2. Beautiful. All right, now the tricky thing. We want to figure out, does the graph cross the horizontal asymptote? So does it cross the horizontal asymptote? Last time it was easy to tell because the horizontal asymptote was where one of the x-intercepts was. But in this case, what you're essentially asking is, does my function ever equal, well, where's my horizontal asymptote? It's at 2. So does my function ever equal 2? Go back to the original before you factored. Okay, f of x was 2x squared plus 4x minus 48 over x squared plus 3x minus 10. And I want to know, does that ever equal 2? If I get a solution, then it crosses. If this equation has no solution, then that means it doesn't cross. So if I multiply both sides by x squared plus 3x minus 10, then we can start solving. So here we're going to have 2x squared plus 4x minus 48 equals, and then I'm going to distribute now, so 2x squared plus 6x minus 20. Look, these are never as bad to solve as you might think. The x squared terms cancel out, and then I have 4x minus 48 equals 6x minus 20, so negative 28 equals 2x. So x equals negative 14. Oh, so what does that mean? Does it cross the horizontal asymptote? Yes. at negative 14, comma, what's the y value where it crosses the horizontal asymptote? 2, because the horizontal asymptote is at y equals 2. Okay, this is exciting. I think we have enough info now to start graphing. So let's go back up here, put our axes down, and we have to go all the way to at least negative 14. So I'm going to scale by 5s on the x-axis and a little more in the negative direction. So plan ahead before you start graphing so it works out for you. Okay, so we're going to say this is 5, 10. Label your axes, x, y, negative 5, negative 10, negative 15. You see that? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. You need not scale both of them by 5. Okay, as long as you're labeling, you can do what you want. It's your world. Okay, let's put those asymptotes down. So we've got vertical asymptote at x equals negative 5 and positive 2. So here's x equals negative 5. And then x equals positive 2. Maybe that's right around there. And then horizontal asymptote is at y equals 2. Good. Now let's start plotting the intercepts. So we have negative 6, 0. So maybe right there. 4, 0. And then the y-intercept is 0, 4.8. And then remember, our graph crosses the horizontal asymptote at negative 14, 2. So I'm going to plot that point there as well. Okay, so there's 3 pieces to the graph. 3 pieces. For the first piece over here, we have to cross through this x-intercept, and we have to cross the horizontal asymptote. And I'm not going to cross the horizontal asymptote again, and I'm not going to cross the x-axis again. So there's one and only way that this is going to look, and I don't need to plot any more points. This is going to come down here. It's going to slowly, slowly approach that horizontal asymptote, cross it, and then you don't need to worry where, but just turn that thing back around. It has a change of heart, and then it approaches the horizontal asymptote the rest of the way. Very nice. Okay, what's going on in the middle? Let me show you options. You tell me yay or nay. We've got a downward parabola like last time. Nay, very wrong, right? Here we are crossing the x-axis. That's not allowed. Crossing the horizontal asymptote. We found all of those points already, so don't make any new ones. It's not allowed. Okay, what about this? Nope. Violation right here. Violation right here. That's not happening. What about the other way? Equally horrendous. Look at that. Okay. Only option left is you have something looking like a parabola opening upward. Where exactly it turns around, I don't know. You know what else could happen too? It could have some wiggles and then it keeps going up. You really don't know until you get to calculus. So right now you can just, draw what you like. Okay, third piece. There's only one option. I mean, this is not happening because we got to cross that x-intercept. This is not happening. You're not approaching the horizontal asymptote. It has to look like 1 over x on those outside pieces, resemble the shape somewhat. So here we go, approaching the vertical asymptote, and it doesn't cross the horizontal asymptote on this side. We found where it crossed the horizontal asymptote, so don't cross it again. That's why we did that step. Okay, I'm emphasizing this so much because students always tell me what a hard time they have putting the graph together. But if you just reason through what makes sense and what you already found, most of the time, the graph reveals itself. If you just think logically about what you're allowed to do. Once in a while, you have to plug in more points like we did in the last one, but not all the time. Okay, good. And hopefully most of the time you get easier problems, but I wanted to show you involved examples. Here we go. Let's take things to the next level. F of x equals x cubed plus 1 divided by x squared minus 9. So we got to factor this. Oh, yes, we do. X cubed plus 1, that's a sum of cubes. Do you remember how a sum of cubes factors? a cubed plus b cubed factors into a plus b times a squared minus ab plus b squared. If you forgot, I'll link a video here about how to factor a sum and difference of cubes. So this is going to factor into x plus 1 times x squared minus x plus 1. Make sure you know how to do that. It's not going away, even when you get to calculus, especially when you get to calculus. And then the denominator factors into x minus 3 times x plus 3. Good. So let's go ahead and list the domain. So the domain is going to be all x's except for, that's right, plus or minus 3. Good. What about x-intercepts? So x-intercepts come from setting the numerator equal to 0. You could set this one equal to 0, but the second factor, x squared minus x plus 1, doesn't have any real zeros. So x cubed plus 1 equals 0. Means x cubed is negative 1, which means x would be negative 1. So the x-intercept is at negative 1, 0. What about the y-intercept? Where's that? So f of 0 is 1 over negative 9. So it's at 0, negative 1/9. Okay. Got some fractions in here. We're kicking things up a bit. Okay, let's see. Vertical asymptotes, do we have any of those? Why, yes, we do. We've got 2 of them at x equals plus or minus 3. And then in this case, notice the degree of the numerator is 3. And the degree of the denominator is 2. Do you remember what this means? If the degree of the numerator is bigger than the degree of the denominator, there's no horizontal asymptote. And if it's exactly bigger by 1, then you have an oblique asymptote. Oblique or slant asymptote, depending on the book. And how do we find its equation? We long divide. Okay, so we talked about this in the previous lesson. I'll link again the video for long division here if you need to review how to do it, but I'll show you the steps right now, but quickly. So you're going to long divide. Remember, f of x was x cubed plus 1 over x squared minus 9. So I'm going to take x squared plus 0x minus 9 and then divide that into x cubed plus 0x squared plus 0x plus 1. For asymptotes, you cannot use synthetic division, especially in this case because you're dividing by something that's not linear, and then in other cases too, it's not going to give you the correct factor at times. Okay, so here we go. Remember, I'm dividing x cubed by x squared, so I'm just going to need an x here, and then I'm going to multiply that out. So we have x cubed plus 0x squared minus 9x, and then I subtract all this. So the x cubes cancel out, which we expected, and then I have 0x squared, so that's gone, and then now a positive 9x plus 1. And then I'm actually done dividing because notice here, x squared is a higher degree than 9x, so we only had 1 round to do there. This is over, this is my remainder, and so the equation of my oblique asymptote is staring me in the face right here. It's the quotient without the remainder, y equals x. Good. Okay, one other thing we need to check is if the graph crosses the oblique asymptote. So before we checked if it crosses the horizontal asymptote, now I want to check, does it cross y equals x? So how do you think we would figure that out? Well, last time we took f of x and set it equal to the equation of the horizontal asymptote, which was a constant. This time I'm going to say, does f of x equal the equation of the horizontal asymptote, x? And we're going to solve. Okay, so f of x is x cubed plus 1 over x squared minus 9. Does that equal x? Let's multiply both sides by x squared minus 9 and see. So here, this cancels. I have x cubed plus 1 equals x cubed minus 9x. The x cubes cancel out. And then that would give me x equals negative 1/9. So yes, it does cross. At negative 1/9, what's the y coordinate? Well, y is equal to x on the slant asymptote or oblique asymptote. So at negative 1/9, negative 1/9 it crosses. Ooh, that's not what I expected. Okay. So there we go. Let's put it all together now. And we'll label everything carefully. There's going to be 3 pieces to the graph because we have 2 vertical asymptotes and that slant asymptote. All right, I'll scale out to 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Same thing in the y direction. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Let's put the vertical asymptotes in. So they are at plus or minus 3. There's positive 3. There's negative 3. Now here's the fun one. So the slant asymptotes equation is y equals x. Do you know how to graph the line y equals x? Slope is 1. Y-intercept is 0. So you graph it, but you graph it the way you would a line, you know, if you were back in Algebra 1, just graphing lines, happy and carefree. But now it's an asymptote, that's all. Let's extend this a wee bit. Okay. Again, there's going to be 3 pieces to the graph. 1, 2, 3. Okay, the vertical asymptotes chop it up into different pieces. So let's see here. For the first portion, we're focusing on it. I'll give you 2 options. You tell me which makes sense. Either it's smashed here between the 2 asymptotes, or sometimes it's like this, all spread out. Which one works? It's going to be the smashed one because this one's crossing the x-axis. That's a no-no. We found the x-intercepts. Oh, I didn't plot them. Excuse me. Let's plot the intercepts. Negative 1, 0. And then 0, negative 1/9 is a y-intercept. Okay. Forgive me for that. Okay, so I know it's not going to cross the x-axis there. So it has to be that first option that's smashed in the middle. You know what? It shouldn't be so sharp. It's curvy. It's curvy. Let's start this again. Now, exactly where, you know, this point is, like I've been saying, don't worry. When you're in calculus, you can fret about all that sort of stuff. But right now, you just get to graph the general shape accurately. Okay, what's going on in the middle? All sorts of craziness, let me tell you. So we've got that x-intercept negative 1, 0. We've got the y-intercept 0, negative 1/9. Also, don't forget, we're crossing the slant asymptote at negative 1/9, negative 1/9. So maybe that's somewhere right here. What in the world? Okay, let's think about our options. We can't have anything parabolic because then it would cross too many times, right? Or if you had something like this, that's crossing the slant asymptote again, crossing the x-axis again. That's not going to be allowed. So the only option that makes sense is the graph is coming this way, crosses, wiggles a bit, and then comes back down. If you want to plot more points so that you feel better about it, go for it. Okay? Very good. I actually want to change this color so they're all the same, right? Let's change this so they match. Much better. Okay, last piece here. I'll give you the options. You tell me which one makes sense. It's all spread out here like this, or it's smashed up here. It has to be the smashed one, right? Look what's wrong with this. Ooh, we're crossing the x-axis. That's not allowed. So it has to be stuck up in here somewhere. Okay. Beautiful. That one's advanced for sure. Okay, a lot of the times they don't do so much crossing and crazy stuff, but now you're ready for anything that comes your way. Last one, are you ready? So sad. These are fun. Okay, f of x equals x squared plus 3x minus 10 over x squared plus 8x plus 15. So we're going to factor completely, numerator and denominator. So we have here x plus 5 times x minus 2 in the numerator, and then in the denominator, x plus 5 times x plus 3. Do you notice something? That's right, you can cancel out x plus 5. So in reduced terms, this is going to be x minus 2 over x plus 3. Now, for most of your computations and everything, you can go ahead and just use the version of f of x in lowest terms. That's completely simplified. However, for the domain, you have to use the original. What do I mean by that? So you still have to list that the restrictions are -5 and -3. Just because you cancel it out doesn't mean it wasn't there to begin with, okay? So there's still going to be a problem at -5. There's not going to be a vertical asymptote, though. No. We're going to have a hole at -5, comma, and I'll show you how to get the y-coordinate in just a second. Okay, now let's go back and get the x and y intercepts. So x-intercept, remember, you can just look at the new reduced form version. When would the numerator be 0? That's right, at 2. So x-intercept is at 2, 0. What about the y-intercept? Can you imagine plugging in 0 for x? You'd get -2/3. And if you went back to the original, that would work also. You'd get -10 over 15. So same thing, it's just easier when you use the one that's reduced or simplified. Okay, vertical asymptotes, you actually only have one. Look at the simplest form, reduced form of the function. So it's at x equals -3. What about horizontal asymptote? You can use the original or reduced form. Degree of the numerator equals the degree of the denominator. So you just take the ratio of the lead coefficients. See, it doesn't matter which version you use. So horizontal asymptote is at y equals 1. And then I promised you I'd tell you how to get the y-coordinate for the hole, right? So the hole has x-coordinate -5. That's because -5 is not in the domain, but it canceled out. So it's a removable discontinuity. You'll learn about that in calculus. To get the y-coordinate, you just plug in -5 for x into the reduced form of the function after canceling. So 5 minus 2 over, -5 minus 2 over -5 plus 3. That's going to be -7 over -2, which is 3.5. So the hole in the graph is at -5, 3.5. And when you plot a hole, you just plot it with an open circle right there. It's like someone came and plucked it out. Okay, we're almost there. See, this one was actually really relaxing. I need to figure out still if it's going to cross the horizontal asymptote. All right, so does this cross the horizontal asymptote? Remember, the equation of the horizontal asymptote is y equals 1. I can use the reduced form of f of x, so x minus 2 over x plus 3. Does that ever equal 1? Well, let's see. That would mean x minus 2 equals x plus 3. Cancel out x, and I get -2 equals 3. That's not true. There's no solution to this equation. So when there's no solution, that means it doesn't cross the asymptote. Good. Now it's time to put it all together. This one's actually much easier than the other ones we've graphed because we only have one vertical asymptote. So x-axis, y-axis, 1, 2, 3, 4, 5. Let's see, the hole is all the way at -5, 3.5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And I'll do a wee bit more. And then 1, 2, 3, 4, 5. Okay. So let's put the asymptotes in. So we've got x equals -3, y equals 1. So there's only going to be two pieces to this graph. And then x-intercept is at 2, 0, 2, 0. Y-intercept is at 0, -2/3. And then whole at -5, 3.5. So just plot an open circle. Okay, so there's two pieces to the graph. This piece has to go this way, right? Approaching the vertical asymptote. We figured out that it doesn't cross the horizontal asymptote at all. So it's just going to behave like this, stay underneath, and that's it. And then the other piece, I for sure know what's going on. So it has to go up this way and then approach the horizontal asymptote here. I know it's not crossing. I know there's no other x-intercept, so that's it. See, it wasn't so bad. Anyways, these take a lot of practice, so be patient with yourself, talk yourself through, and worst case scenario, you can always plot more points, but the beauty is most of the time you don't have to. So you can make a really awesome graph just by following the steps and using some deductive reasoning, if you will. Anyways, that concludes the lesson, so please give it a thumbs up. Don't forget to subscribe if you haven't already, and then we have more fun with polynomials and rational functions coming your way.